Hello all, and welcome to our video on Chapter 4, Section 4, entitled Curve Sketching. As I mentioned in class, what we're going to do in this section is mostly just collect information and processes that we have learned in previous sections and even back to college algebra, and put them all together in achieving this goal of sketching a curve, making a sketch of a curve, the graph of a specific function. Okay, so in this video I'm going to move through this pretty quickly. So one thing that you might find helpful is to follow along in the book starting on page 225 so you can look back and forth more easily as I refer to things that are not on the screen anymore. As we go through this list. Also, like I said, I'm going to move pretty quickly, so I would encourage you, probably more than usual, to take advantage of pausing and rewinding this video to make sure that you are following everything that we're doing, that you understand each step as I go through them. Okay, so let's begin. When we have a function of x, and we are wanting to graph that function where y is the function value as usual, we want to sketch that graph by hand, okay? Not using any kind of graphing tool, calculator, or anything online. We just want to sketch that graph. And again, our graph is not going to necessarily be exact. That's why we call it sketching, but we do want it to be reasonably accurate, to give us a reasonably accurate idea of the shape of the graph. Especially certain details. Okay, so what do we look at first? First we look at the domain. Okay, find the domain of the function. Okay, which means the set of x values for which the function is defined. So that's pretty basic. Then we move on to intercepts. The y-intercept is where x equals 0, so we can find that by plugging in 0 for x. The x-intercepts and a function can only have one y-intercept, because it has to pass the vertical line test. It can have multiple x-intercepts, however. In fact, it can have an infinite number of x-intercepts. To find the x-intercepts, we set the function equal to 0 and solve for x. And if we have a function that's difficult to solve or perhaps even impossible, then we just skip that step and don't worry about the x-intercepts. But if we can find them, they are helpful to find. Okay. Next thing is we talk about symmetry. And we did mention this briefly in class. We saw an example that we recognized as an even function. If we have a graph that's an even function, meaning f of the opposite of x is the same expression as f of x, they are equivalent, then the curve is symmetric to the y-axis. Okay? So that means we only have to graph the part of it on one side of the y-axis, and we know the other side will be a reflection of that. So as it says here, that cuts our work in half. If we have, okay, so there's an example. If I had this function and I could determine that it was even, then all I would need to do is graph points and other things on the right side, and then when I was done I could sketch the left side to be a reflection of that. Also, a function could have symmetry if it is an odd function, meaning if we take f of the opposite of x, we get the opposite function value. So then we have an odd function, and the graph is symmetric about the origin. Okay, so we'd have this situation. Again, we cut our work in half. Once I know what's happening to the right of the x-axis, I can just fill in the left side to be a rotation of that about the origin. So rotational symmetry is what we have there. Another situation is we can have a periodic function. Okay, if we add some value to x and we always get the same function value no matter what x is for some fixed value p, then that is called a periodic function. And as we hopefully remember, the most common examples of periodic functions that we deal with regularly are trigonometric functions. So if we had a trig function, that would be periodic. Okay, and that number p is called the period. So for example, the period of the sine function is 2 pi. So if I just graph it from 0 to 2 pi, I know exactly what's going to happen on all the domain, on all the real numbers, because I can just continue repeating that same graph, that same shape, over and over and over again, once I've determined what it is from 0 to 2 pi. Okay, next thing that we look at are asymptotes. Horizontal asymptotes are found by taking the limit of the function as x approaches infinity. That will give us a horizontal asymptote to the right, or the limit of the function as x approaches negative infinity. That will give us a horizontal asymptote to the left. Okay, now if either one of those limits are infinity or negative infinity, then we do not have a horizontal asymptote, but we do know something about the curve. If we have a limit of infinity, that means, whether we were going to the right or to the left, the function is increasing without bound in that direction. If our limit was negative infinity, then we know the function is decreasing without bound, whichever way it was, if it was on the right or if it was on the left, if x was going to infinity or if x was going to negative infinity. Okay, so even though we don't have an asymptote, we do know something about the shape of the curve from that limit at infinity being infinity. Okay, and then what's even more common and more useful is the vertical asymptotes. We have a vertical asymptote if we have a limit as x approaches a finite number from the right or left, or of course if we have a two-sided limit, that means it's approaching the same thing from the right and the left. If that limit is infinity or negative infinity, then we have a vertical asymptote. Okay, and again, how do we most commonly see vertical asymptotes? If we have a rational function and the denominator could be 0. X values that make the denominator 0 will show vertical asymptotes in our graph, but there are also other situations where you have vertical asymptotes. For example, the tangent function or cosecant function, some of our trig functions, or the log functions. Log functions have a vertical asymptote as well. So it's not going to be only the denominator being 0. So we need to look for all of those. Okay, the next thing we look for is where the function is increasing and decreasing, and that is using exactly what we just did in section 3. So we don't need to go over that in detail. We do the increasing decreasing test using the first derivative, and from there we can find local maximum values. Okay, local maximum and minimum, local extremum, local extrema. So again, we find the critical numbers and we test whether the function's increasing or decreasing on both sides. Okay, one thing to point out, it's come up a couple times and I've talked to some students about it individually. If we have a value for which the original function does not exist, the original function is not defined, meaning this value is not in the domain of the original function, then that is not a critical number. Now it may be a place where the function changes from increasing to decreasing, but that's going to be something like a vertical asymptote. So even though, let's say I have this graph right here, okay, let's say I have a vertical asymptote, okay, and my graph looks like that. Okay, well that's a bad example. Let's say my graph looks like this, okay? So on the left side it's increasing, on the right side it's decreasing, okay? So when I state the intervals increasing and decreasing, I definitely, let's say this number is 3. I definitely have to test both sides of 3. Okay, negative infinity to 3 and 3 to infinity. I have to separate those into two different intervals to test for increasing and decreasing. However, even though the function is increasing here and decreasing here, do I have a local maximum? No, because the function does not exist at x equals 3. So there is no point to be that local maximum. Both sides of this are going to infinity. Okay, the function value is going to infinity on both sides of 3. So it does change from increasing to decreasing, and we need to know that, but we need to remember that does not mean it's a local maximum in this case. Excuse me. Okay, so when we use that first derivative test, we have to keep that in mind. That only works for numbers where the original function is defined. Okay? Even if we change from positive to negative, we may not have a local maximum, because if that number is a place the original function is not defined, like if it's a vertical asymptote, we will not have a local maximum. Okay. We can also use the second derivative test if we choose, but since we're already having to find intervals of increasing and decreasing, it really makes the most sense to just use the first derivative test because the information is right there, literally already. Okay. So, next thing we look for is concavity and points of inflection, which again we learned just in the last section, in section 4.3, and we use the second derivative of the function, and we talked about how to do that. So we go through that process, and then that's the last step. After that, we are ready to sketch the curve. Okay, so that's the last step of preparation. Then we sketch our curve. We draw in our asymptotes as dotted lines. We plot all the points we know, so any x or y intercepts, any extrema, maxima and minima, local, and any inflection points. Okay, so sometimes, depending on the function, that might not give us a lot. That might only give us 1 or 2 points, or sometimes, depending on the function, that might give us many points and give us a very accurate view of the shape of the graph. Okay, so then we connect those points and make sure we're following the information we discovered about where the function's increasing and decreasing, where we have asymptotes, and what the concavity is. Okay, and we even really mentioned that in class last time. Be careful when you're drawing that. Okay, if we still don't have enough information to get an accurate idea of the shape of the graph and a reasonably accurate idea of the shape of the graph, we can plot more points. Simply plug in more x values into our function to get more points. Or we can look at the value of a derivative at any point if we want to see how sharply the graph is rising or falling at that point. We can look at the value of the derivative because that tells us the slope of the tangent. Okay, excuse me. Let's take a look at an example then, and I've summarized or listed our steps, just a short word for each one, to remind us what steps we go through to sketch this curve. Okay, so here's example 1, this function right here. Okay, well, let's start with the domain. What is the domain of this function? Well, when we're finding domain, we start by assuming the domain is all real numbers and look for what we have to exclude. And what are really typically, other than functions that we know the domain of, like log function or a tangent function or a secant function that we know where the asymptotes are, other than those more specific functions, what do we look for to exclude from the domain? We look for any x values that make the denominator 0. So that's what we have here. Okay, where does x minus 1 equal 0? When x equals 1. Okay. The other thing we look for is where we have a negative value inside of an even root. Well, we don't have any roots here, so that's not going to be an issue here. So our domain excludes just the number 1, everything except the number 1. Okay, so now let's look for intercepts. Let's start with the y-intercept, which we find by doing what? By plugging in 0. F of 0 is 0 over 0 minus 1, so that's 0. Okay, so we see the y-intercept is the origin, 0, 0. And the x-intercepts are going to be where the function equals 0. Well, again, this is a fraction. This is a rational expression. So the fraction will be 0 when the numerator is 0. Okay, 0. Well, we already knew that the point 0, 0 was there because we found it as the y-intercept. So it is, of course, also an x-intercept. But we see there are no other x-intercepts. There's no other x values that make the numerator 0. And when we plug in 0 for x, we see that the denominator is not 0. So that still is exactly what we need it to be in order to say that 0, 0 is our only x-intercept. Okay, so far we found one point, the origin, That's both our y-intercept and our only x-intercept. Now let's talk about symmetry. Well, let's see what we get when we plug in negative x into the function, or the opposite of x. We get this. Is this equal to the same as the original function? No, it's certainly not. If I multiplied the top and bottom by -1, or divided the top and bottom by -1, I'd get x over x plus 1. That's not the same as x over x minus 1. I also don't get the opposite of this. Okay, the opposite of this would be negative x over negative x plus 1, not negative x over negative x minus 1. Okay, so, and it's certainly not periodic. So there is no symmetry. Okay, when we are doing our problems, we need to do whatever is the relevant work for each step, whatever is the necessary work, and we need to write down what we found. Even if our findings are nothing, we write down no symmetry, or no points of inflection, or no intervals increasing. Okay, we write down whatever we find to make that clear. Okay, so that's it for symmetry. Now let's look at asymptotes. Okay, let's look at horizontal asymptotes. What's happening to x over x minus 1 as x goes to infinity? Well, if we remember our shortcut, we look at the degree of the numerator and denominator. Both of them are degree 1. So what is the limit as x approaches infinity? Again, this method, this shortcut is only useful, only possible to be used when we're finding a limit as x approaches infinity or negative infinity. Okay, well, since x is approaching infinity, our limit will be the ratio of the leading coefficients. Well, again, both of them are 1, just like both of the degrees are 1. So we have 1 over 1, the limit is 1. And what if we put in negative infinity there? Well, then we get negative 1 over negative 1. Okay, we still get positive 1. Negative 1 over negative 1 gives us positive 1. Okay? Okay. So we see on the we see that we have a horizontal asymptote. Okay, at what line? Y equals 1, and that is the horizontal asymptote in both directions, as x goes to positive infinity and as x goes to negative infinity. Okay. Now, they ask us to find where the function is increasing and decreasing. Okay, which means we need to find what? We need to find the first derivative. Won't that be fun? And I just realized my computer is not plugged in, and that could lead to some very negative consequences, so let me plug it in. Okay, now I'm plugged in. Okay, so we're finding the intervals of increase and decrease. That means we need our first derivative. Why is that not writing? That's weird. Okay, so we've got y equals x over x minus 1. We need to use the quotient rule, or that's the most obvious option, to differentiate. So the denominator times the derivative of the numerator times the numerator times the derivative of the denominator over the denominator squared. Okay, and when we simplify that, we get negative 1 over x minus 1 squared, because these x's on the top cancel each other out. Okay, so what are our critical values there? Critical numbers. Well, we see this cannot equal 0 because the numerator is negative 1. No x values are going to make this fraction equal 0. Where does this fraction not exist? Okay, it does not exist at x equals 1, because that makes the denominator 0. Now, is x equals 1 a critical number? Could x equals 1 be an extremum? No, because the original function is not defined at 1 either. That was not what I wanted to do. Okay, the original function is not defined at 1 either, as we noticed in our domain. Okay, so it's not a critical number in the sense that it cannot be a local maximum or a local minimum. However, it can still be a place where the function changes from increasing to decreasing, or vice versa, like the example we looked at. Did I erase that already? Like right here, okay? Because in this function, x equals 1 is a vertical asymptote. Okay. Oh, I forgot to do vertical asymptotes. Ha 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 ha. How am I going to squeeze that in here? Let me try this. This may not work. Oh, I think it did. Awesome. Okay, so I forgot to do vertical asymptotes, not just horizontal asymptotes. Okay, well, vertical asymptotes for this one are pretty easy. As we just said, we have a vertical asymptote at x equals 1 because 1 makes the denominator 0. Okay, and that's the only way we can get 0 in the denominator. So for this rational function, that's the only vertical asymptote. Okay, so it'll probably be good for us to identify our answers here too. There's our domain. Here's our y-intercept and our x-intercept, which is really the same point. There is no symmetry. We have a horizontal asymptote at y equals 1 in both directions. And we have a vertical asymptote at x equals 1. So I guess asymptotes was not appropriate. Okay, so what do we need to do here? We need to use our first derivative test. So again, our function needs to be separated into negative infinity to 1 and 1 to infinity. And we look at the first derivative. Okay, the first derivative is negative 1 over x minus 1 quantity squared. Well, what do we notice about that? X minus 1 quantity squared will always be greater than or equal to 0. Okay, it cannot be negative. So negative 1 over x minus 1 quantity squared will always be less than or equal to 0. Okay, it will always be negative because we have a negative over a positive, assuming that we don't have a 0 in the denominator. Okay, so both of these are negative, which means in both cases the original function is doing what? Yes, it is decreasing. Okay, so our answer is the function is decreasing on negative infinity to 1 and on 1 to infinity. Okay, and again, it wouldn't really be accurate to say the function's decreasing everywhere, or the function's decreasing on all real numbers, because it's not defined on x equals 1. So we need to make that clear, even when we talk about functions, intervals increasing and decreasing. Okay, well now I've gotten way down from my summary up here. Next thing was local extrema. Well, as we already said, since the only place the first derivative is 0 or does not exist is a place that the original function does not exist, and since it's decreasing on the left and on the right, we know that there is no local extrema. There are no local extrema. Okay, and then the next thing we're to do is to find concavity and points of inflection, and that of course involves the use of the second derivative. Okay, so now I need to differentiate my first derivative. And I notice I have negative 1 over x minus 1 quantity squared. I could certainly use the quotient rule again, but when I see that, especially with a negative 1 in the numerator, I recognize that that is the same as saying negative x minus 1, x minus 1 to the negative 2 power. I take it out of the denominator and make the exponent negative. Okay? Okay, so that's my f prime of x. That's my first derivative. So now that I have it in that form, I can differentiate it by simply using the chain rule. Okay, so the negative coefficient stays the same, and and then this exponent comes down, so that's a negative 2, times x minus 1 to the negative 3, using a chain rule and the power rule together. Negative 2 minus 1 is negative 3. Be careful when you're subtracting from negative numbers that you don't go the wrong direction. And that has to be times the derivative of the inside function. But the inside function is x minus 1, and that derivative is just 1. So what do we have? The opposite of negative 2, that's positive 2. This is a negative 3 exponent, so I'll say this is 2 over x minus 1 quantity to the third power. Okay, so we see again, what's the only place this could equal 0? Well, it can't equal 0. There is no place the second derivative cannot equal 0. There is no place the second derivative can equal 0. So all we're going to look for is places the second derivative does not exist, which again is of course 1. Does not exist at x equals 1. But again, the original function does not exist at x equals 1. So this cannot be an inflection point. So we actually can already see there are no inflection points. But it could be still a place where the concavity changes from the left side to the right side. So let's go ahead and test it. We still need to test our we need to test the values of the second derivative to check our concavity. Okay, so again we're going negative infinity to 1 and 1 to infinity, and I probably didn't leave enough space on the left. Let's just rewrite that all. Okay, negative infinity to 1 and 1 to infinity. And what is the second derivative? Okay, well again, the numerator is always positive in the second derivative, isn't it? Okay, so let's say I plug in 0. Well, then I have 0 minus 1, that's negative 1. 2 over negative 1 cubed. Negative 1 cubed, 3 is an odd power, so the result is negative. I get 2 over negative 1, which is a negative number. What if I plug in 2? Then I have 2 over 1, 2 minus 1 quantity cubed. Plug in 2 for x. So I have 2 over 1 cubed, which is just 2, positive 2. So I see that the function, the graph of the function, is concave down from in negative infinity to 1 and concave up from 1 to infinity. Okay? So I'm going to go ahead and write that out, because that is the way I get full credit on my homework or on a test. Okay. And also, that's not the only reason. We also do it because it makes what we're saying very clear and well organized and easy to read. Okay, so now what? That's all we have to find. Now we're ready to sketch our graph. Okay, well let's look at what we know. We know the function goes through the origin, and that's the only points we have because there are no local extrema and there are no inflection points. Whew. But we do know there's a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 1. Okay, well I think I have enough to figure out how to make my axes. I don't really need to go to big numbers, so I'm actually going to mark off, just to make this easier to see, 2 boxes as a unit. Okay, so every 2 boxes is a unit as the little lines indicate. Okay, so what do we know? We know the function goes through the point 0, 0. We know there is no symmetry. We know that there is a horizontal asymptote at y equals 1. Okay, and that's the horizontal asymptote to the right and the left. So it serves 2 purposes. There's a vertical asymptote at x equals 1. Okay. And that's all we have there. Okay, what about the first derivative? It tells us the function is always decreasing. And it tells us then that we of course have no local extrema. This function is always decreasing. Okay, and the last thing we learned is that to the left of 1 it is concave down, to the right of 1 it is concave up. And again, to be clear, this function is decreasing everywhere. Okay? So I don't really have a lot of information here, so what I would probably do is get a couple more points. Okay, so for example, y at x equals 3 is oh wow, that was nice. is 3 over 3 minus 1. That's 3 halves. Okay? So that's going to be 1 and a half. Okay, so that's going to be that point right there. What about at x equals negative 2? Okay, that gives me negative 2 over negative 2 minus 1. That gives me negative 2 over negative 3. That's positive 2/3. Okay, that gives me positive 2/3. So I have the point negative 2, positive 2/3 as another point. Okay, and I can plug in more points. If I plug in 2, I get 2 over 1. Okay, if I plug in negative 1, I get negative 1 over negative 2. That's positive 1/2. Okay, and so on. So I'm starting to get an idea of the shape here. What we have here is a hyperbola. Okay, one type of hyperbola. Okay, I know this is going to be going down to negative infinity. Okay, and how do I know that? Because I know that this function is decreasing on its domain. Okay, so it's always decreasing as we move left to right. So this is the only direction to make the lines go that makes sense. Okay, and that's it. That's what we get. Okay, remember, when you have sparse information, when you've gone through the whole process and you still don't have that much information, just plot some extra points to get a better idea of the shape of your graph. Okay. Alright, well, there's one example. As I said, they take a lot of time, don't they? Let me just see how long we've been going. Oh, 31 minutes already? Oh, that's so oppressive. Okay. You know what? Let's just stop this video. That's one example. We'll take a look at another one in class. I might this weekend make another video. If I do, I will email you and let you know, just to see another example of this. And we'll do probably one example in class. Like I told you, an example takes like 20 to 25 minutes, even a relatively straightforward one, especially when it's a new process. So, yeah, see you in class, next class, and if I make another video with another example of this curve sketching process, I'll send you an email also, so be checking your email this weekend. Thanks very much. Have a wonderful day. Talk to you later.